Welcome to the world of Python multiprocessing. In this video, explore how to run tasks in parallel to fully utilize your computer's central processing unit, also known as the CPU. Let's understand what multiprocessing is all about. Multiprocessing is a Python module that lets you run your code at the same time, which is known as parallel execution. It achieves this by using multiple CPU cores, which are like the brains of your computer, by creating separate processes. Multiprocessing helps to get around the limitations of something called the Global Interpreter Lock, or GIL. It is best for CPU-intensive tasks. So, why should you use multiprocessing? First, it speeds up CPU-intensive operations, which means your code runs faster when it needs a lot of processing power. Second, it uses all the available processor cores in your computer. And third, it gives you better performance than using threads for CPU-intensive tasks. Here is a simple multiprocessing example. First, we import the process module from the multiprocessing library. After that, we define a worker function that simply prints a message with the worker's name. Then, inside the if __name _= _main block, we create a list to hold our processes. Next, we create 4 processes, each running the worker function with a different number, from 0 to 3 as its name. Then we start each process, which makes them run in parallel. Let us learn about process pools. A process pool is a way to manage a group of worker processes effectively. It helps you run multiple tasks at the same time using a set number of processes. Here on the left is a basic example of a process pool. First, we import the pool class from the multiprocessing module. Then we define a function called process_task that takes a number x and returns its square. After that, inside the if __name == main block, we create a pool with 4 processes. Then we use the pool.map method to apply the process_task function to a list of numbers from 1 to 5. Finally, it prints the results, which will be the squares of the numbers 1, 4, 9, 16, and 25. Here's another way to use process pools, using something called process pool executor. First, we import process pool executor from the concurrent.futures module. Then we define a function called process_item that takes a number x and returns its double. After that, inside the if __name == main block, we define a list of numbers called data. Next, we create a process pool executor and use its map method to apply the process_item function to the data list. Lastly, it prints the results as a list, which will be the doubled numbers 20, 40, 60, and 80. Now, explore how to share data between different processes. When you're working with multiple processes, it is sometimes necessary for them to share data. There are different ways to do this in Python's multiprocessing module, each with its own advantages. Here's a look at some of these methods. Value. This is used for sharing simple values like numbers or characters. Array. This is used for sharing arrays of values. RARray/RAValue. These are similar to array and value, but they don't have any built-in synchronization, which means you need to be careful to avoid race conditions. Manager. This creates proxy objects for more complex data types like lists or dictionaries. Queue. This is a thread and process safe first in first out, FIFO queue, which is useful for passing messages between processes. Here's an example of how to use shared memory objects. First, import process, value, and array from the multiprocessing module. Then define a function called update_shared_data that takes a counter and a data array as input. Inside the function, it first increments the counter value by 1, using a lock to prevent race conditions. Then, it iterates over the data array and multiplies each element by 2. After that, inside the if __name == main block, we create a shared value object called counter and initialize it to 0. Next, create a shared array object called data and initialize it with the values 1, 2, 3, and 4. Finally, create a process that runs the update_shared_data function with the shared counter and data array as arguments. Let's find out the best practices for multiprocessing. First, protect your entry point. Always include if __name__equals _main___ in your code to make sure that the multiprocessing code only runs when the script is executed directly. Second, use process pools for CPU-bound tasks. Process pools are great for tasks that require a lot of processing power. Third, minimize data transfer between processes. Sending large amounts of data between processes can slow things down. Fourth, properly terminate processes with join. Use the join method to wait for processes to finish before your main program continues. Fifth, consider process count based on CPU cores. A good starting point is to use one process per CPU core. Sixth, use locks when accessing shared resources. This prevents multiple processes from trying to modify the same data at the same time, which can lead to errors. Here's a real-world example of image processing. We import the pool class from the multiprocessing module and the OS module. Then define a function called process_image that takes an image path as input. This function simulates processing an image by printing a message with the image path. After that, inside the if __name__equals block, we define a list of image files. Next, we get the number of CPU cores using os.cpu_count. Then we create a pool with the number of processes equal to the CPU count. After that, we use the pool.map method to apply the process_image function to each image file in the list. Finally, prints a message indicating that all images have been processed. Now let's explore some advanced multiprocessing techniques. First, process communication with pipes. Pipes provide a way for processes to communicate with each other in both directions. Here is a code example. First, we import process and pipe from the multiprocessing module. Then we define a function called sender that takes a connection object as input. Inside the function, we send a list containing a string, a number, and another string through the connection. After sending the data, we close the connection. After that, inside the if __name__equals block, we create two connection objects, parent_con and child_con, using pipe. Next, we create a process that runs the sender function with the child_con as an argument. Then we start the process. After that, we receive the data sent by the sender process using parent_rect and print it. Finally, we wait for the process to finish using p.join. Second, process synchronization. Locks are used to prevent multiple processes from accessing shared resources at the same time, which can cause race conditions. Here is a code example. We import process, lock, and value from the multiprocessing module. Then we define a function called increment that takes a counter and a lock as input. Inside the function, we loop 100 times. In each iteration, we acquire the lock using a with statement, which ensures that only one process can access the counter at a time. Then we increment the counter value by 1. After that, inside the if __name__equals block, we create a lock object and a value object. The value object is used to store a shared integer counter. Next, we create 4 processes, each running the increment function with the shared counter and lock as arguments. Then we start each process. Let's do a performance comparison. Here is a comparison of processing time for a CPU-bound task using sequential processing, threading, and multiprocessing. The processing time using sequential processing is 10.2 seconds. The processing time using threading is 9.8 seconds. And the processing time using multiprocessing is 2.6 seconds. Here are some key takeaways. Multiprocessing provides a significant speed up for CPU-bound tasks. Threading shows minimal improvement due to Python's global interpreter lock. Optimal process count typically equals CPU core count. Overhead increases with more processes than cores. And for input-output bound tasks, threading may be more efficient. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.